Hello everyone, I'm J Wildberger. In this famous math problem, we are looking at the following very important issue. How do you actually construct the true complex numbers? This, of course, is a very central topic in mathematics. It's been studied for hundreds of years. From initial rather shaky foundations, people have now put this in the center of a lot of mathematical discourse. But the actual foundational issue of how you actually construct complex numbers in the first place has not, in my view, been adequately and properly addressed. As a result, we have a rather limited view of the subject. We think that complex numbers are an extension field of the real numbers, very specific, focused kind of thing, based on ultimately a kind of, vague or maybe more precisely fake arithmetic of real numbers, where you just pretend that you can do all these arithmetical operations that you really can't. So we're separated from actual computational reality. The true complex numbers are found in a different direction, where we have to look at things more generally, more broadly, and more algebraically. And no infinite processes are even required or indeed desired. So as far as I'm concerned, this is up till now an unsolved problem, and basically I'm giving you the solution of how to think about complex numbers in the right way. Okay, so the crucial thing is to define this dihedron algebra. So we start with a field. Okay, so F is a field in great generality. And then the dihedron algebra is the algebra of 2 by 2 matrices with entries in the field. And we'll denote that by D. Now, it turns out that this is what we're going to call a quadratic inverse algebra over the field F. It's an algebra with a multiplicative quadratic form. And that multiplicative quadratic form controls inversion in the field. So I'm aiming towards explaining what's going on here. This will be a very general, powerful point of view towards complex numbers that allow us to see that there's not just the usual complex numbers, but there are two other ones which are relativistic versions, which are every bit as good and important mathematically as the usual Euclidean complex numbers. So this is a big step up in your understanding. And if you're an undergraduate, you really want to listen very carefully to what I'm saying here and learn it all. Now, a basis for this space of dihedrons, it's a four-dimensional space over our field. A basis for it is given by these important four matrices. So the identity matrix, which is usually called capital I, but we're going to just denote it with a 1. And if necessary, we might make this 1 just a little bit bigger or bolder than usual to remind you that this is our basic identity matrix. And then we have I, J, and K, written also in terms of our spanking new notation. So instead of writing minus A, we'll rather prefer to write A with an overline above it, so A bar, to represent negative A. So the matrix I is 0, 1, negative 1, 0, or 0, 1, 1 bar, 0. J is 0, 1, 1, 0, and K is 1, 0, 0, negative 1, or 1 bar. So these are very analogous to the quaternions that were introduced by Hamilton in the middle of the 19th century. And the relations are as follows. I squared is equal to negative 1, or 1 bar. J squared equals 1, and K squared equals 1, where these ones here are meaning this identity matrix. And then we have relations between them. So I times J is equal to K, while J times I is equal to K bar, or negative K. J times K is equal to I bar, and K times J is equal to I. And K times I is equal to J, while I times K equals J bar. So you see there's something a little bit different about I. J and K are a lot the same. I is a little bit different. So these two rows are sort of similar, but this row here is a little bit different because it involves I in the space where J and K are previously. So please check these relations, a bit of practice for your matrix multiplication in the 2 by 2 case. Okay, so now we can describe a general dihedron as a linear combination of these basis elements. So let's say D for dihedron is T times 1 plus X times I plus Y times J plus Z times K. And then when you write out what that means, you get this 2 by 2 matrix whose entry here is T plus Z, because the 1 and the K are the things contributing to the diagonal. So we get T plus Z here and T plus Z bar, or T plus negative Z down here. And then in the off diagonal places, we get X plus Y up here and X bar plus Y down here. So this is a typical dihedron, not written in the form A, B, C, D, but rather with respect to this particular basis, which is particularly important for this discussion. Now, sometimes it's convenient to just shorten this. Instead of writing it out as a combination, we just write it out as a 4-vector with the coefficients t, x, y, and z, with respect to the basis ordered this way. Now, there's an alternate way of thinking about what a dihedron is, that is separating the t part from this part here. So the I, j, and k can perhaps be thought of as 3 vectors in a 3-dimensional space that's more familiar to us. So what we have here is actually sort of t plus a vector v, where this vector is the vector x, y, z in a 3-dimensional space over the field. This is a very compact way of representing things, which captures the distinction between the identity part and the sort of the vector part. So there's a scalar part here and a vector part to the dihedron. And this is entirely analogous to what happens in the usual familiar story of quaternions. Now, I'd like to explain why we call these things dihedrons. Okay, it's because there is a connection with a finite group with 8 elements called the dihedral group. And that group is sort of sitting inside our algebra when we take our 4 basis matrices, 1, I, j, and k, together with their negatives. Okay, so I'll put plus or minus here. Okay, so plus or minus 1, plus or minus I, plus or minus j, plus or minus k. So it's all together 8 things. And when you look at the relations that I showed you on the previous slide, you see that these 8 are closed under multiplication. So we just look at this as a set under multiplication. It's closed under multiplication. And in fact, it turns out to be a group with identity, this thing here, and inverse elements, which you can deduce from the relations. In fact, this is one of only 2 groups of order 8 which are non-commutative. Okay, there's commutative groups which are sort of simpler. They're products of cyclic groups. And then there's non-commutative groups. And when we look at the order 8 groups, there's actually only 2 of them. And they are this dihedral group and the quaternion group. Okay, so again, this parallelism between the dihedrons and the quaternions is manifesting itself at the level of the connections with finite group theory. So you should think about these 2 are sort of on the same level. Quaternions, dihedrons, they are sisters. Okay. Now, I want to remind you that one way of thinking about what a matrix is in terms of a linear transformation. And you have a choice whether you want to think about a matrix acting on row vectors by multiplying on the right, or acting on column vectors by multiplying on the left. And it's just a choice of taste. So let's consider just the action of matrices on row vectors. This is just how you multiply this 1 by 2 matrix with this 2 by 2 matrix. You get AX plus CY for the first entry and BX plus DY for the second entry. So multiplying by a fixed 2 by 2 matrix transforms vectors in 2-dimensional space, sends a 2-dimensional vector to another 2-dimensional vector. That's one way of thinking about the meaning, the geometrical meaning of a 2 by 2 matrix over a field. So when we think about it this way, then these 8 matrices that are occurring up here have a very specific role in what they do in the plane. And I want to illustrate that with this little diagram here. So this is a 2-dimensional vector space with, say, typical element xy. So here is a vector xy represented either by a point or by this vector emanating from the origin. Okay. And let's call that vector v. And now if we multiply by various elements here, we're going to get different vectors. So for example, if we multiply by 1, which is the identity matrix, well, we're not getting anything different. We stay where we are. However, if we multiply by j, let's say j is 0, 1, 1, 0. If you put in 0, 1, 1, 0 here, you'll see that xy is sent to yx. Okay, so the effect of taking this vector and multiplying by j is to give you yx. If you multiply by k, you get x minus y down here, the reflection in here. If you multiply by I, you get minus yx, which is like perpendicular to this one here. So going from here to here is actually a reflection in this line. Going from here to here is a reflection in this line. And going from here to here is a rotation by a quarter turn, or 90 degrees. And what about the negatives? Well, the negatives are just the reflections of these 4 in the origin. So this is the original vector, and here is negative that vector. Here is the vector multiplied by j. Here's the vector multiplied by minus j. Here's the vector multiplied by minus k, and here's the vector multiplied by minus I. So these 8 possibilities show exactly the effects of these 8 matrices acting on a typical starting vector xy. Now there's another way of describing that in terms of symmetries of a square, which is usually a more elementary geometrical way of describing the dihedral group. It doesn't require any linear algebraic framework. We just start off with a square. And we say, okay, this square has certain symmetries, such as what? Well, such as, say, rotation by a quarter turn. That's a symmetry of the square. We could call that rotation I. Or maybe we could have the symmetry, which is reflection around this diagonal. So these 2 vertices are left the same, and these ones here swap places. Or this one here, which is reflection in this horizontal axis, sends this to this and this to this. Okay, so and then the negatives are sort of the obvious things when negative means you reflect in the origin. So then in this context here, these 8 things correspond to the 8 symmetries of a square. Okay, so this dihedron group or dihedral group, okay, can be thought of either this way or this way, and that is why we're calling the algebra of 2x2 matrices the dihedron algebra, because right in the heart of it is this group of order 8. Exactly parallel to the quaternion story, where the quaternion algebra, 4-dimensional algebra, has at its heart this quaternion group of order 8. Completely analogous stories. So to appreciate why the 2x2 algebra of dihedrons is such a central object in mathematics, we have to appreciate the role of 2 functions on this algebra, the trace and the determinant. Okay, so if you have a typical dihedron, A, B, C, D, let's call it R, not D. If I call it D, then there's a possible confusion with that entry there. So let's call it R temporarily. Okay, that's a dihedron. Then we're going to define T of R to be 1/2 its trace. The trace of a matrix is just the sum of the entries down the diagonal. So this is A plus D over 2. And we'll call this map or function the half trace of the dihedron R. Okay, that's the half trace. Notice that if we start with the identity matrix, then the half trace is 1. Trace is 2, but the half trace is 1. Okay, and then the second important quantity is what we're going to call Q of R. Q of R is the determinant of this 2 by 2 matrix, which is AD minus BC. And we're going to say that's the quadrants of the dihedron. Okay, so we're introducing two quantities associated with a dihedron. Its half trace, capital T, and its quadrants, capital Q. Now, if you know anything about rational trigonometry, you know that quadrants is a central foundational concept in rational trigonometry, sort of the building block of the whole thing. So this is certainly suggesting that we're touching base here with rational trigonometry and geometrical issues. And that's exactly what's happening. So it's really very important to appreciate that this quantity, this determinant here, is, in this 2 by 2 case, a quadratic form. It's a quadratic function of the entries of the matrix. Only in 2 dimensions do you have this crucial property happening. Doesn't happen in 1 dimensions, doesn't happen in 3, 4, or higher dimensions. Only in dimension 2 is the determinant a quadratic form. That's like $1 million insight. Really fundamental thing to appreciate. Why the 2-dimensional situation, this 4-dimensional algebra of dihedrons, plays such an important role. It has a lot to do with the fact that the determinant is actually a quadratic form. And the crucial property about the quadrants is the familiar property that determinants have, which is their crucial property, that they are multiplicative. The determinant of a product is the product of the determinants. So in our language, Q of D1, D2 equals Q of D1 times Q of D2 for dihedrons D1 and D2. All right, so this is a crucial property, which is just a rewriting of the determinantal property that actually holds for any size matrices. Okay? But it's especially important here because this is actually a quadratic form in this 2-dimensional situation. Now, if you're a typical undergraduate, you're probably thinking, why hasn't anybody told me this? Why don't I hear about this in my standard courses? The role of geometry in modern mathematics, unfortunately, has diminished quite a bit in the last few decades, last century. And so the geometrical aspects of algebraic things are often not quite as appreciated as they were in former times. Okay, so we're kind of going back to a more geometrical understanding of algebraic issues. That's very important for complex numbers because complex numbers are every bit as geometrical as they are algebraic. Okay, we're bringing the algebra and the geometry together here. So if you have a metrical geometry, which is typically described in one of 2 ways, either by the idea of a symmetric bilinear form, sometimes called a dot product, or by a quadratic form, which is a quadratic function. Okay, so these are 2 different ways of thinking about metrical geometry, and it's well known that they're closely connected. If you have a symmetric bilinear form, say u dot v, then associated to it immediately is a quadratic form, where you just define the quadrants of a vector to be v dot v. Instead of having a function, a linear function of 2 vectors, you have a quadratic function of 1 vector. That's sort of a simple-minded way of saying it. But crucially, it's also well known that you can start with the quadratic form and recover the symmetric bilinear form, which is completely determined by it. And this way of doing this is called polarization, and it's all involved in this identity here. If you take the quadrants in this sense of the sum of 2 vectors, u plus v, then that's going to be u plus v dot u plus v. And then the symmetric bilinear form aspect is going to be u dot u plus v dot v, and then you get a u dot v and a v dot u. And because of the bilinear form, we're assuming it is symmetrical, that's the same as 2 times u dot v. And now you stare at this, you see, we can now determine this dot product because this thing's actually a quadrant, this is a quadrant, and this is a quadrant. In other words, we can solve for u dot v to get 1/2 of the quadrants of u plus v here, minus the quadrants of u, minus the quadrants of v. So this is the well-known polarization formula that allows you to recover the bilinear form or symmetric bilinear form that gives rise to a quadratic form. So a natural question for us is, okay, in this two-dimensional situation, the determinant is this sort of God-given quadratic form. So what is the associated symmetric bilinear form? Right? That's the kind of thing that you think about if you're a geometer. It's like a completely obvious question. How do you write down the symmetric bilinear form that's giving us the determinant in this special 2x2 case where we actually have a quadratic form? All right, so let's do a calculation using that polarization formula. So here's a dihedron, and here's another one. A1, B1, C1, D1, A2, B2, C2, D2. This mystery dot product that we're trying to determine is 1/2 of the quadratic form applied to the sum. So the quadratic form we're talking about is just the determinant. If you take the sum of these two matrices and you take the determinant, you're going to get A1 plus A2 times D1 plus D2 minus B1 plus B2 times C1 plus C2. Like AD minus BC, where each of the entries is the sum of the corresponding two over here. And then we have to subtract the quadrants of this one, which is its determinant. In other words, A1 D1 minus B1 C1. And you also have to subtract the quadrants of this thing, which is its determinant, which is A2 D2 minus B2 C2. And happily, there's quite a lot of cancellation when you just expand all these things out and simplify. You get 1/2 of A1 D2 plus A2 D1 minus B1 C2 minus B2 C1. This is a bilinear form. It's linear in this matrix entries. So there's an A1, a D1, a B1, and a C1. So as a function of this, it's linear, and it's also linear as a function of this thing. How can we write this nicely? Well, one way is to use our T, our half-trace function. And we write it as the first matrix, A1, B1, C1, D1, times a certain other matrix, and we take the half-trace. And the certain other matrix that you have to cook up has to be this one in order for it to work out. So if you take the product of these two matrices, and then you take the half-trace, you're going to get 1/2 of the top entry here will be A1 D2 minus B1 C2. A1 D2 minus B1 C2. You're getting exactly these two terms. And the term in the bottom right will be minus B2 C1 plus A2 D1. Minus B2 C1 plus A2 D1. So yes, indeed, if you take the half-trace of this product, you're getting exactly this value of the symmetric bilinear form. So we've figured out what the symmetric bilinear form is that's associated with the determinant in the 2x2 case. And it's essentially given by this new kind of object, which turns out to be the classical adjoint or adjugate of a matrix. So this is a concept that's been around for a long, long time. The adjugate of a matrix A, B, C, D is D, A. So the two diagonal elements get swapped. And B bar up here and C bar down here. The off diagonal elements get multiplied by 1 bar or minus 1. They are negated. And we're going to introduce the following important notation for this adjugate. By the way, adjugate, in ancient times this was called the adjoint, or sometimes the classical adjoint, which is actually, in my view, probably preferred notation. But these days the adjoint means something different, okay? And that's a bit unfortunate. But in any case, we're going to use star here. It's really going to be important for us. This is such an important operation on 2x2 matrices. And so we're elevating its importance by giving it this star name. Okay, so the star of A, B, C, D is D, B bar, C bar, A. So the adjugate has a number of important properties. So for D1 and D2 dihedrons, the adjugate of D1 times D2 is D2 star times D1 star. So it's the product of the adjugates, but in the reverse order. That's something that you can check. And this proposition captures what we've basically just figured out. Then this symmetric bilinear form, that D1 dot D2 is by definition T, the half trace of D1 times D2 star. That is a symmetric bilinear form on the dihedrons with associated quadratic form, our quadrants form, which is the determinant. So the associated symmetric bilinear form to the determinant in the 2x2 case is given by this symmetric bilinear form. It's half trace of D1 times D2 star, where star is the adjugate. Another important calculation is what happens when you multiply a matrix by its adjugate. So ABCD times ABCD star. Please check that you're getting a multiple of the identity matrix. You get, in fact, the determinant AD minus BC times the identity matrix 1, 0, 0, 1. So this certainly suggests that there's going to be an interesting connection between notions of invertibility and, well, this geometrical point of view. We'll talk about that more in our next video. So another proposition is what it actually looks like in terms of our preferred basis. So if we take a dihedron of the form T times 1 plus X times I plus Y times J plus Z times K, which we've seen has this form as a 2x2 matrix, then its adjugate, D star, is T times 1 plus X bar times I plus Y bar times J plus Z bar times K. In other words, the T stays where it is, but the other three all get negated. The Z here and here get negated, so we get Z bar and Z, and the X's and Y's all negated. So we get X bar plus Y bar up here, and X plus Y bar down here. So at the level of dihedrons written in terms of our canonical basis, this adjugate is a very pleasant thing. Okay, so now let's introduce conjugation on dihedrons. Okay, so conjugation is just going to be another name for this adjugate operation. So if D is equal to T plus V, it's a dihedron in our very compact scalar plus vector form, then its adjugate or conjugate D star is T plus V bar, which we can also write as T minus V. So that is the conjugation, what we're going to be calling conjugation, on the entire algebra of the dihedrons. So to connect that with our complex number story. Our complex number story is obtained by slicing this four-dimensional algebra of dihedrons with a two-dimensional plane, which includes the identity matrix and gives us a commutative little subalgebra. And we've seen that there are three basic slices: the blue one, the red one, and the green one. In the blue case, we're looking at matrices of the form A, B, B bar A, which we can write in terms of our basis as A times 1 plus B times I. And now if we star this one or conjugate it, same as conjugating this, then what happens is just that the coefficient of I is negated. We get A plus B bar I, which you could also write as A minus BI if you introduce subtraction. So at the level of the usual complex numbers, we see that yes, indeed, we're getting what is usually called conjugation. For the red story, a red complex number typically looks like this: A, B, B, A, which we can write as A plus BJ. when we take the conjugate of that kind of thing, well, this b negates, so we get a plus b bar j, which is a minus bj. Very similar kind of form as we got in the blue story. And in the green one, well, here's your typical green complex number, a plus b, 0, 0, a plus b bar, or otherwise a plus b times k. We take the conjugate of those, we get a plus b bar k, which is a minus bk. So in each of the three situations, the conjugate is looking like the familiar conjugate that you're used to with ordinary complex numbers. But each one of these three stories, then the theory of each one of these stories is really just a restriction of this bigger story on the dihedrons. Okay, that's what's happening, is that what we usually think of as, a complex number story is really just the restriction of this bigger, more general, more powerful story on this entire algebra of dihedrons. And you can restrict to the blue or the red or the green equally well. They're all legitimate, beautiful subalgebras of the dihedrons. So there's a strong symmetry between these three things, and we really want to investigate them all at the same time. Okay, so we made a good start, a lot of content in this video. Go over it carefully. In our next video in this series, we're going to show more how this geometrical orientation, okay, to complex numbers really controls a lot of what's happening in the theory of complex numbers. Hope you'll join me for that. I'm J Wildberger. Thanks for listening.